stuck together. So an example of two atoms, right, over there on number 16 on the second row, the big red O, is oxygen. It's an element. It's also an atom. If I take two oxygens and join them together, I'll get O2. That's a molecule, right? Because they are two of the same things bonded together. But you can also take a hydrogen, you can bond it to an oxygen, and if you give yourself two hydrogens, now you have a molecule of water. But now I've got different atoms bonded together. Right? So molecules are either the same or a collection of atoms that are bonded together. From math, right? Compounds are a subset of molecules. So in other words, all compounds are molecules, but not all molecules are compounds. Because to be a compound, you have to have two or more different things to make that substance. They have to be different. If they're the same, then they can be a molecule, but not and they can also be a compound.
So all molecules are compounds, but not all compounds are molecules?
No, all compounds are molecules, but not all molecules are compounds.
Yeah.
Now, with that is back into elements. You know, they're a group of atoms. But now we want to know, well, what is an atom? If I break an atom down, I no longer have its identity. Right? If you break apart me in my individual parts, you no longer have John. You'll have two lungs, a heart, stomach, intestines, right? Eyeballs, ears, ears, excuse me. Right? So when you take an atom and break it down, you say, well, what is it actually made up of? Well, an atom is made up of something called protons, neutrons, and electrons. That's what makes up an atom. And yes, when you go into Chem 161 and Chem 162 and maybe parts of 139, you'll learn about other more subatomic particles, smaller, teenier, tinier, more annoying things, known as quarks and neutrinos, and on and on and on. All right, so an atom is really, it's a very complicated thing. It's really, really teeny, teeny, tiny. And what I want to stress right now as we get into talking about this is that if you could get down to the size of an atom, then the space in between its various parts, like between its protons and electrons, is ginormous. It's like you being in San Francisco and the other part of your structure is in New York. It is huge in terms of the scale of an actual atom itself. Now, what are these things called protons, neutrons, and electrons, and where do we find them? All right, so I divided this slide into two things. Right? Located in the nucleus, in blue, two things, protons and neutrons. But down here, located outside the nucleus, we're going to have electrons. All right, so that's my first level of learning. And maybe what you want to do as you learn new things is approach it in like an onion. First, my first layer, got that, cool. I'm going to peel off that and get a little more specific, get down to the next layer. So your first job is just memorize those three things that make up an atom. The word proton, neutron, electron. I've got that. Awesome. Now I'm going to memorize which one's located where. Neutrons and protons in the nucleus. Whatever they are, I don't know what they are, but they're in the nucleus. And then the electrons. Whatever they are, they're not in the nucleus. They're outside of it. Okay, cool. I've got that. Now I have another layer. Protons have an electrical charge of +1. All right, you add that to your layer of understanding. Neutrons, right? Neutron, neutral, meaning they have no charge. They're zero. They're like neutral. Okay. Electrons have a -1 charge. All right, so we've got lots of things to kind of keep track on this one slide. I know protons are in the middle, and they have a positive charge. Neutrons are also in the middle, but they're neutral in charge. Then these things that are outside the nucleus called electrons that have a -1 charge. All right, cool. I'm happy with all of that. Right? So you'll describe this to your dog, your cat, your friend, whoever you're going to be teaching to. Now, what about, give me a picture. I'm more of a visual learner, right? I never do read the directions to IKEA furniture. I just look at the pictures if I can't figure it out on my own, right? Because pictures speak 1,000 words, and they give you something else to look at besides just a bunch of words. Here's a picture of what we just learned, right? There's the nucleus, my protons, my neutrons, and then there is outside the nucleus, known as the place where I find my electrons. Now, what's different between this picture and this one? Well, this one may be how you were taught about chemistry in high school, where the electrons orbit around the nucleus. So if you want to maybe kind of help you, maybe draw a little cloud or a circle around here, so you realize that this blue line does not represent the actual nucleus itself, but this is a path around the nucleus. But if you look at the picture, it seems like the electrons go around and around and around, like a, what's that thing? A merry-go-round. Well, we know that's not true. This is a better picture. Wherever there's blue, there could be an electron. So what I want you to think about is electrons don't orbit around the nucleus. Think of them like you notice moths attracted to light at night. It's going to fly this way and around that way and around this way and around that way, but it is limited in terms of how far away it can go. But I'm kind of stuck in orbiting like this. I can go anywhere and everywhere. I just can't go past a certain distance. Like there's an imaginary, like for dogs, invisible fences, right? Where the dog won't want to pass that certain distance from home, it gets shocked. Well, electrons can't go past a certain distance under normal conditions. This is what's called a cloud of electrons, meaning these guys could zoom anywhere around in here, they just can't get further away. And then you'll get into this a lot in Chem 161. Okay, well then what makes really, when we mentioned the word sodium and oxygen and hydrogen and chlorides, what makes them different? Why is sodium and all these guys different? Well, it comes down to really the amount of protons and neutrons that are in their nucleus. Alright, so if each atom or each element that are different from each other have different numbers of protons and neutrons, then we can look at the periodic table, and in the 1700s this guy's had a brilliant idea and he arranged all the elements in order from the smallest to the biggest. That's why you have over here, hydrogen has the number 1, has 1 proton. This guy has 2 protons. That guy has 3, or that gal has 3, that thing has 3, that one has 4, that one has 5, 6, 7, 8, and they go on and on and on and on and on. And they're just listed in order. Which is really actually that's going to help you figure out who can interact with who as you get into chemistry. So what makes them different is the number of protons and neutrons. All right, now, the atomic number is that number in black in the upper right-hand corner. That thing right there. All right, that's its atomic number. And so if that one says 10, it's going to have 10 protons and 10 neutrons in it. Way down over here, 103, has 103 protons. Right now, this is an outdated periodic table. As of December 30th, 2015, we go up to 118 now. Because we've made them, or we've discovered them. Right? So even this now is outdated. But the one called 118 would have 118 protons in it and 118 neutrons in it. Right? It would be a big honking heavy atom, or a big honking heavy element. Yes. It can also be different. We'll get there. Hang on. Okay. All right, now, so here's a cartoon to represent that, right? Hydrogen has 1 proton, it'll have 1 electron. Carbon, number 6 over there, right? It'll have 6 protons. It will also have 6 electrons as we go through them. And nitrogen and oxygen. All right, so here's a nice little summary. And even this periodic table is not up to date. This one only goes up to, well, same as that one. Well, no, it's small, 110. This one's really outdated. But it like, gives you a picture of an atom or of an element. It shows you the protons and the neutrons and the electrons, and has definitions of them over here. All right. As I already just showed you, that if the atomic number now tells me how many protons, and that will also equal the number of neutrons, I now also know that it equals the number of electrons. Which means overall, for an atom that has no charge to it, it's neutral. Because if it has, let's give it the number of oxygen for number 8, so here's oxygen with the number 8 on it. It's going to have 8 pluses in the middle of it. Right? And it'll have 8 negatives on the outside of it. Right? So that means they cancel each other out. There's overall no charge. If you have 118 protons, you'll have 118 neutrons and 118 electrons. 118 negative things and 118 positive things, right, equals 0. No charge. They're all balanced. Now, where do I find those electrons? Well, they're not all in the same place. They are in layers, like floors to a building or layers of an onion. When you look at an atom here, let's look at carbon. All right, it has 6 protons, that's number 6. It has 6 electrons. All right, I know that. So you're going to learn this in Chem 121 or in Chem 139. If carbon has 6 electrons, I need to place them in their appropriate energy levels. So here's the rule. The very first orbit, or the very first energy level, can only hold 2 electrons. That's it. Only 2 seats. So I take 2 of my 6, and I put them in that first orbit, in the first layer. How many do I have left over? 4. Those will go in the next orbit, because the next orbit can actually hold 8, a total of 8. And so can the third, and so can the fourth. But the first one can only hold 2.
If you have just 6, how are you going to put 8?
Well, you can't. Exactly.
Yeah.
And that's a cool point. That's why there are these little empty circles. Because carbon is going to want to have 8 in its outer shell. All right? So it wants 8, but you only got 4. All right? So you're still missing 4 more. All right? Nitrogen. If you look over here, there's nitrogen, right? Number 7. 7 protons, 7 neutrons, and 7 electrons. Let's place those electrons. 2 of them automatically go in the first layer. I have 5 left over, right? The next layer, the next orbit can hold 8. I've only got 5. So I place my 5. 1, 2, 3, 4, 5, which means I can hold 3 more, right? Now, here's another cool thing with periodic table of elements. They're listed in order from the smallest to getting bigger, 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 and bigger, to biggest, right? But also, if you look at them, hydrogen has 1 electron. It only has 1 orbit. And that 1 orbit wants 2, but it only has 1. 1 total orbits, 2 total orbits. The first one has 2. The second has whatever number are remaining. We know this one had 5 in its outer shell, right? Because we gave 2 for the first orbit. It wants 3 more, right?
Yeah.
1, 2, 3. Where you find them down here in terms of the row tells you how many electrons it needs to complete its outer shell. If you're over here with lithium, you have 2 orbits, 1, 2. The second orbit only has 1 electron in it. It needs 7 more. 1, 2, 3, 4, 5, 6, 7. So everybody in here has their outer shell totally filled up. They have no more room. And by knowing that, it helps you figure out what are the chances of this combining with that. Well, Chloride has 17 protons, electrons. Its outer shell, I can tell by its position in the chart, it needs one more electron to be complete. Potassium only has one in its outer shell. Potassium chloride very easily forms together. Because when they come together, they form a complete outer shell. They're like soulmates in a sense. All right? So let's look at how we do that. The energy of a single electron. All right, and just to give you an idea of how small these things are, those of you in Chem 121 may have to memorize these numbers. Those of you in Chem 139 who plan to go to Chem 161 will have to memorize these numbers. But for example, I forgot, speaking of remembering, proton weighs 6.77 times 10 to the minus 24 grams.
Memorize that?
Yeah. Avogadro's number 6.02 times 10 to the 23rd. Right. An electron weighs 9.7 times 10 to the minus 24th. You just, like I said, right, if you keep going over and over, you'll never forget whether you want to or not. All right? But think about it, that means that it's going to be this number with 24 zeros actually in front of the 6. And the decimal point goes way over here. All right, so 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Bottom line, incredibly small, right? Really, really teeny, teeny, tiny, tiny. All right, so let's go back to our orbits for a second. I now know that the first orbit, the first shell, can only hold 2. Any additional orbits, for right now, for us to keep it simple, will hold 8. And you get into 121, you'll find out there's a certain limit to that truth, all right? Now, this orbit is closer to the nucleus than this orbit is, right? All right, so the closer you get to the nucleus, in terms of how much energy you find in those electrons, the closer to the nucleus, those guys have less energy. Those that are further away have more energy. And the further you are, the more energy you have in those electrons. So again, when you get into chemistry, you realize I can look at the rows, row 1, row 1, row 2, row 3, row 4, row 5, row 6, row 7, right? That there are 7 layers of electrons. These guys have a whopping amount of energy in their outer shell compared to the ones that are in these guys' outer shell. Because there are more layers, right? So the further you get, the more energy they have.
Right.
Energy for making bonds or explosions, whatever you want or need the energy for. Okay.
That's how you make it.
Now, the outer shell, as we've already said, wants to have 8 electrons. It may not have 8, which means that atom will do whatever it can do to make sure it has 8. All right, it can either gain, it can either take from somebody, or it can share. Okay. Now, atoms will give up an electron or electrons, or will gain an electron or electrons, or it'll share them. It'll do whatever it needs to do to make sure it has 8 in its outermost shell. All right, now, when 2 or more atoms are together because they are sharing or exchanging, they form what we call a chemical bond. So when you take electrons from someone, like, give me, this is mine, I now have 1 additional electron. Right? She has lost 1, but we have formed a chemical bond. Or we can share. All right? Now we both have that same electron. That makes a chemical bond as well. And we have words to describe those different methods. Being greedy and taking, or being nice and sharing, gives us different types of chemical bonds. All right? So, now we can have a picture and realize, right, first shell or the first row, second shell or the second row, third shell or the third row, right? 1, 2, 3. Sodium is right there. That's the first column, which means it only has 1 in its outermost shell. There's the 1 in its outermost shell. Right? That thing tells you a lot, and it'll be your best friend in chemistry. And you can read an awful lot from it, make a lot of good assumptions based upon it. You do not need to memorize any of the elements in here, except for maybe, you know, like, well, we'll do them when we get to them. I'll say, know this one for sure. But don't begin to try and memorize this slide at all. This is a visual, so lets you see how we can tell how many electrons are around the atom and in its orbits. All right? But now, have you ever heard of an ion? Like a sodium ion, a potassium ion. All right? Well, how are ions different than atoms? Or different than elements? Well, we know atoms, right? If you go back to oxygen, number 8 over here has 8 protons, 8 neutrons, and 8 electrons. The 8 electrons cancel out the 8 protons. It has no charge. If I steal one of those electrons away from it, it has one more proton than it does electron. We're now off balance. We have a charge. That's what an ion is. It's an atom that's either gained or lost an electron. It no longer equals the number of protons. So over here we have sodium, which would be number 11 on our periodic table. It's in the first row, which tells me its outermost shell only has 1 electron. Chloride, right, way over here. It is in the 7th row, which means it has 7 electrons in its outermost shell. It's only short 1. And you go, oh, you need 1. In a sense, you have 1 too many. So now what's easier to do? To gain 7 or to give up your 1 so that your outermost shell now falls down a layer, but it has 8 in its outermost layer. Right? If I get rid of this one, and this orbit disappears, this becomes its outermost orbit. And it has 8 electrons in it. It's happy. Right? The rule is I want 8 in my outermost. Whether I got to get rid of my outermost to make 8, or I got to take on something to my outermost, I'm going to do that. This one's going to take on 1 additional electron. That one's going to give up 1 additional electron. Both become ions. They've gained, they've lost. Right? And here we're trying to show you that. It's missing 1 electron, or it needs 1 more for the 8 to be complete. So if this one were to try and steal it, then sodium now has 2, 4, 6, 8 in its now outermost shell. Chloride now has 2, 4, 6, 8 in its now new outer shell. Both are happy. Right? And they're stuck together because a positive charge is attracted to a negative. They form a bond. This is what we're going to call an ionic bond, because ions are bonding, ionic.
How did sodium become positive and chloride become negative?
Right, so we're going to have, so sodium number 11, it's going to have 11 protons, so we'll do it this way, 11 protons that are plus charge. It'll have normally 11 electrons, negative charge. Overall, 11 pluses, 11 minuses gives me a 0 net difference, right? Right. Now I still have 11 protons, but now I only have 10 electrons. I have 1 more positive than I do negative.
Okay.
So sodium goes from being neutral to having a positive charge.
Okay, I was thinking it.
Ah.
Yes.
So which one of them is an ion? The sodium
Both.
or the chloride?
Both.
Both of them are?
Both. Right.
They come together.
So in order
And make
to know what
love.
elements can combine, we're looking at which 2 elements can fit together to make
They make
the
love.
electron.
Yeah, exactly. So think about carbon, and we'll end with this and start with this again on next Friday. Carbon is right here, right? It's in the 1, 2, skip all these guys, all right? 1, 2, 3, 4th row. It means it has 1, 2, 3, 4 more electrons it needs. I'm halfway. I can either get rid of my 4 or I could gain 4. And gaining 4 makes carbon a universally used atom. It'll make lots of bonds with lots of things, right? And we'll start with that.